everyone, welcome back. So we are learning the lesson Boolean Algebra, and from the previous lessons we are learning the various laws. And today's is going to be the last session on the laws. So let's go ahead and see what are those. So the first one is the absorption law. Now what does this law says? According to this law, x plus xy is equal to x. So you can see that whenever we are doing a OR operation with x and xy, we will get x as an output is what this law is saying. Okay. Next, the second law of absorption law is saying x into x plus y is equals to x. So let's see what is the logic diagram looks like. Okay. So here we have x and xy. So this means first we need to do the AND operation between x and y. So that is what we are doing. We are taking x and y as an input. So here this x only has been given as an input here and y. So we will get xy. And then again this x has been given as an input to another OR operator along with the output of this AND. So xy and x we will get, so here this is x, we will get x plus xy. Okay, so see the logic diagram here for this particular rule. So it is saying x or x plus y. So first we need to do the x plus y operation. For x plus, here plus is nothing but or. Okay, so that's what we are doing. X and y we are giving as an input to the or operator, hence we are getting x plus y. Now I am doing the AND operation with x. So I am getting x into x plus y, which is nothing but x according to this absorption law. So let's go ahead and prove these laws. So the first one is x plus xy is equal to x. So let me take the left hand side. I'm taking the left hand side and I'm saying x is equal to x plus y. Now I'm taking the common term out, which is x. Now what happens here? Only 1 plus y remains, isn't it? Now from the law of from the rule of OR operator, we know that whenever we do a OR operation of any Boolean variable with 1, we will always get 1 irrespective of value of y. Okay, so that is what is happening. So 1 plus y becomes, this entire thing becomes 1. And again, from the law of OR operator, we know that whenever I am doing from the law of AND operation, we know that whenever I am doing a AND operation of any Boolean variable with 1, I will always get the variable. So x and 1 becomes 1, which is nothing but my right hand side. Hence, this is proved. I hope this is clear to you all. Okay, let's see the truth table for the same. I'm taking x value, I'm taking y value. First, I will do x and y. So 0, 0 becomes 0, 0, 1 becomes 0, 1, 0 becomes 0, 1 and 1 becomes 1. Now I'm doing OR this entire thing OR with x. So what happens now? This one with this, I have to do OR operation. So what I will get? 0, 0, 0, 0, 0, 0, 1, 0, 1, 1, 1, 1. So see here carefully. So this is nothing but my left hand side, which is this and this same, right? So x plus xy is similar to x. Hence, we have proved from the truth table also that this law is correct or this law is proved. Clear? So let's go ahead and prove the next one. So let me take the left hand side, okay, which is nothing but x into x plus y. Let me open this, let me multiply this. What happens? X into x plus x into y, right? Now again, I will take x common. What will be there? 1 plus y remains inside the bracket. Now what is this? 1 plus y is nothing but 1. Okay. From the rule of AND operation, we know that x into 1 is always x. Okay, so hence we will get the value x, hence this is proved. Fine. Now let's go ahead and draw the truth table for this and see if this holds good with the truth table also. So we need two variable truth table. So Let me write x and y. Okay. So since it is a two variable truth table, how many rows we are going to have? We are going to have 4 rows. 1, 0, 1, 1. First we need is x plus y, right? So how do we get this x plus y? We need to do a OR operation between x and y. Let's go ahead and do that. So 0, 0 we will get 0, 0, 1 we will get 1, 1, 0 we will get 1, 1, 1 we will get 1. So we have x plus y. Now we need to do the AND operation between this column and this column. Okay, so let's go ahead and do that. X into x plus y. Okay, so what happens now? 0, 0 will be 0, 0, 1 will be 0, 1, 1 will be 1, 1, 1 will be 1, right? Now observe here carefully, is this column and this column are similar? They are, isn't it? Hence what we are trying to say is this entire expression is nothing but equal to x. Hence, we have proved this also using the truth table. Okay. So this is all about absorption law. So next we are going to see some other rules of Boolean algebra. The very first one is this one where it is saying x plus x bar y is nothing but x plus y. Okay. So this is also called as third distributive law. Now how do we write a diagram for this or a logic gate for this? See, we are doing a OR operation here where we are giving x and x bar y as an input. Now for this x bar y, we have one is for bar we need a NOT gate, and between these two we have a AND gate. Clear? So first let us go ahead and do the diagram for this, which is x bar y. How do we get a x bar? Okay, so we have a x. When x is given as an input to the NOT operator, we will get x bar. Fine, we got x bar. Now we need to do it AND operation of that with y. That's why we are giving y and this as a input to the AND operation. Hence we will get this, which is x bar y. Clear? Now since we got this, we are going to do a OR operation of these two, which is x and whatever the output we got from this AND operation. So when we are giving this x and x bar y as an input to this OR operator, we will get this. Now according to this law, what is it saying is this entire thing is similar to this, which is nothing but x and y. That is what this law is saying. Okay, so let's go ahead and prove that. First, I'm going to take the left hand side, which is x plus x bar y. Okay, so now from the distributive law, already we know that x plus yz can be written as x plus y and x plus z. This we learned in the last session, isn't it? So we are going to use this here. So how we are writing x plus x bar y here, this one if you take it as y and this one if you take it as z, apply the same rule, we are going to get this expression. Okay, so we will get this. Now this one we know that x into x bar is always 1 from the properties of OR operator. So that's why this entire thing becomes 1 and this remains same. And also from the properties of OR, we know that any variable OR with 1, we will always get the same variable. That's why we are getting x plus y here, which is nothing but our right hand side. Okay, that is why we have, hence we have proved this theorem. I hope it is clear. Now let us see the truth table. So since we are taking two values, we are having 4 rows. First, we need x plus y, which is nothing but our right hand side. Okay, so x plus y is nothing but OR operation. So 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1. Next, let's take x bar, which is nothing but complement of this entire row. So 1, 1, 0, 0. Next, I am doing AND operations of x bar with y because I need this one, right? So when I do AND operation of x bar with y, I will get this value. Now the final expression, which is this one or x. When I do, I will get this column. Okay. Now observe carefully. Is this entire column and this one is same? Isn't it? This is nothing but my right hand side and this is nothing but my left hand side. So since these two are similar, we have proved using the truth table also that this rule is proved. Okay. So this was the third distributive law. So we have till now we have learned so many rules and laws and theorems. So I have all put it together in a small table. So let's see them one by one. The first one was properties of 0, where we saw 0 plus x is equal to x, 0 and x is 0. Next one was properties of 1, where we said that 1 when it is ORed with x, we will get 1, and 1 when it is AND with any variable, we will get the same variable. These are idempotence laws. This is our involution law. These are our complementary law. This also we saw it in the last session. Then we have our commutative law, the two laws. Then we have associative law, the two laws, distributive law, both of them, absorption law, and then the last laws. Okay, this one was the the third distributive law which we saw just now. Okay, it is important for you to remember these laws. Okay, so you may ask why we require this. What is the purpose of learning all these laws? Okay, so the main thing is we are going to use them in order to reduce our Boolean expressions. Now, again, you will ask why we need to reduce a Boolean expression. Okay, so suppose uh, uh, the main reason of reducing a Boolean expression is they are helpful in building the logic gates. Now, these logic gates are the building blocks of our CPU. So whenever we reduce a particular Boolean expressions, which means we have reduced the logic gates, which in turn we are reducing the expenses. Okay. So suppose I have an expression x bar, y bar, the whole bar. So how do you write a logic gate for this? First, you need a NOT gate in order to get a X bar, and then you need a um, uh, NOT gate for Y bar, isn't it? And then you are going to do AND operation of these two, and whatever output you will get, again you need to do the NOT of that. So there are so many involved in this, so many things, but this is also equal to what? This is nothing but our x plus y, isn't it? And how do we do that x plus y? All you need to take x, you need to take y, and then you need to do a OR operations. So see how complicated is this and how simple is this. So that is where these Boolean expressions reducing is required. Okay, so for that we need all these laws, and this is going to be very helpful. So instead of using 4 gates, we can do the same work using 1 gate. So this is reducing cost, this is reducing time, and this is helping us in simplifying our efforts, isn't it? So that's all in this today's session, students. So we are going to see De Morgan's theorem in the coming session. So thank you for watching.